have a function f. We have a closed interval from a to b. And we like to know the point, or if you take that lambda, which is a surface of uniform density, and try to find the center of gravity or the centroid, depending on whether or not you're looking at it from a physicist standpoint or a geometric standpoint. And we found that x bar is basically the moment about the y-axis divided by the area, and y bar is the moment about the x-axis divided by the area. And if you want to be completely accurate, you have to have the density times the area, which is the mass, and the density times the moment. And if you have uniform density, then obviously these two divide out. And if we're looking at the moment about the y-axis, look at the y-axis here and the x-axis here. You're looking at that moment about the y-axis, and you're looking at the composite area here, then we know it's the sum of the products of the x-coordinate of the centroid times the area. And so, in terms of a curve, we have the integral from a to b. Not getting large enough there. Maybe integral from a to b. We're looking at the moment, then we're looking at the x distance out here, the x coordinate of that. I use wiggle here, and y coordinate. So the x coordinate times the area, which is the function dx. So here's your area. Here's your distance to the x coordinate of the centroid. Then again the area, which we simply have as f of x dx. Then what I wanted to do was to keep it all in terms of x. So we looked at yesterday the vertical strips, which, if you look at this area here, think of this as dx, and this is h of x. Then the y coordinate then is 1/2 the upper curve plus the lower curve, which in this case would be the x-axis. And this is what allows us then, when we're looking at y bar, to keep this all in terms of have that same area, but the integral we have in the numerator is still from a to b, and in this case we have then in general f plus g times f minus g dx, and we have the half out here, and last time this is the calculation that I missed. And as any good algebra student knows, that you can handle this as the sum and difference, which gives you the difference of the squares here. So it basically boils down to f squared minus g squared for the integrand. And we've taken the easy case. The easy case is where you have uniform density, and the more general case is where rho is a variable density. In other words, it may vary as the distance from the x-axis or the y-axis, the density of. And if that changes, then, as they like to say in textbooks, it's beyond the scope of the single integral, and you have to go to the double integral, which, if you fall in love with calculus, then you'll take another course and figure out how you can use the double integral. We're so happy just to handle the single integral that we're not going to go on. That basically summarizes all you have to set up for the centroid, or the center of gravity, depending on how you're looking at it. And I think it's much better to keep it all in terms of from A to B. In other words, if we went the other way and did it this way, then we'd have to go from C to D. We would have to integrate with respect to y and change all the things around. Since we have this set up, this is the easiest way to do it. and I gave you some problems, and I'll talk about those probably on Friday if we're having any trouble. I think we'll try to line things up on Friday with problems and things we're doing. The thing that I'd like to do now is to say, well, I think this is something that's probably been haunting you as you're going through this, and that is we have different techniques for integration, and even in this situation here, that all assumes that you can find the anti-derivative here. And most of our physical applications have been built on the fact that we've approximated or thought of the definite integral from a to b of f of x dx. We thought of that as the area under curve, the area of this region, if you will. And everything in the fundamental theorem of calculus says this is equal to capital F of x evaluated from a to b, which is equal to f of b minus f of a. And this is all predicated on the fact that you can find what? A function whose derivative is this little f here. And I'm sure since we started this thing, it's haunted you in terms of what happens if I can't find this capital F of x. Now this has happened on several occasions, only because you couldn't find it, you didn't know the function whose derivative was that. And now what I want to come up with is a technique for evaluating this definite integral if you can't find this capital F of x, which is an approximation technique, which has become very, very popular. Well, approximately evaluating the integral from a to b of f of x dx. How are we going to do it? Well, we're going to do the same thing as we did with setting up this. We're going to take the integral from a to b, and we're going to break it up into subintervals, x0, x1, x2, up to some predetermined xn. And we're going to, in taking these subintervals here, when we did the area of the region, we used rectangles. And if you have an increasing function in this interval, then obviously, or maybe it isn't so obvious, but it is, the approximation, especially if I use that last one, the approximation using rectangles is pretty coarse. In other words, it's much too large if you use circumscribed rectangles, and by the same reason, if we use inscribed rectangles, it would be too small. So we'd like to refine that if we're actually going to have to approximate this thing. Refine it. The first refinement that we're going to use is to approximate it now as a rectangle, but with something that gets a little closer to this and approximates it in terms of what would this pose figure be if I put this pink segment in here, right? Trapezoid. And this is the name of the first approximation, the trapezoidal approximation. And that brings up then the formula for the area of a trapezoid. The area of a trapezoid is equal to, what is it, Mr. Sork? You have a trapezoid. You know what I know? 1/2 the height, that's a good start. Use it again. Half the height, then times what? Sum of the bases. B1 plus B2. Now this is our basic idea then. So what we're going to do is take this interval, break it up into subintervals, and use the approximating idea of a trapezoid. So if we're looking at the area of this region here, the area of the region, we could call this, with the pink boundary here, trapezoid 1, trapezoid 2, up to trapezoid sub n, the last one. So, in looking at a approximation, we'll approximate that by the sum of the trapezoid. So that if we're trying to evaluate this integral from a to b of f of x dx, and this is a function that we can't find the antiderivative for, or there's no nice capital F for the fundamental theorem, then we're going to approximate it by taking the sum of the trapezoid from I equal 1 to n. Take the sum of those things as our approximating idea. Now, using this set of subintervals then, if we look at the first trapezoid here, we call A x0, x1, x2, and finally B is x sub n. Then we can think of these heights here as f of x0, and we can look at this one then as f of x1, and this one as f of x2. And what's the role of the, and finally f of xn. What's the role of each of these segments here going to be, Mr. Eisen, relative to our area of our trapezoid? In other words, the question is whether it's H or B1, B2. Well, look, you got to look at these things. Let's take a one representative picture out of here. If I put it like this, I put this pink, see there, then what's the B1, B2? They're the parallel sides. So this, say this is f x0, this is f x1. See, so these will be the length of the B1, B2 of our formula. And then what's H in our picture here? Pardon? No, that won't be H. H is the distance between these two parallel sides. So it's going to be delta X. It's going to be the delta X. See? So in this case, this is going to be our height. These are going to be the lengths of our parallel sides. So if I think of this as T1, if I think of this as T1, then my first trapezoid will be 1/2 delta X times what sum then? What will be B1, B2 of my first trapezoid? Yeah, f of x sub 0. Right. So I have, so I don't have to write this every time. Call it f sub 0 and f sub 1. What's going to be my, so that's my T1. T2 then would be, Robinson, if I look at this thing now and change this, that'll be 2, this will be 1, this will be 2, so
yeah, 1/2 delta times f 1 plus f2.
And due to the restriction on the board space here, notice if I take these two here and add them up, if I add these things up, first of all, I can take what? Common factor 1/2 delta X out. And if I combine these first two terms, what will I have?
0 plus 2x1 plus
And as I go to T3 here, then what am I going to pick up for this f sub 2? Mr. Eisen? I'm going to have 2 of these, and I'm going to continue this until I get down, and then finally I'll have the last one, which will be 1/2 delta X. Now, what will the f values be for the last one then in general? f of n minus 1 plus f of n. Right? So using the idea of the trapezoid and the sum of those trapezoids, then I can look at my formula. The area of the region is approximately 1/2 delta x times, what will the first base be, value that I'll put in there? Or first one that I'll have. So I start adding those up. F0. I'll have F0 plus, the next one that'll be certainly 2F1 plus 2F2 plus, what will the last double be in this array here, since it's a finite number though?
2F1 minus 1.
Right, F sub n minus 1 plus finally F sub n. And this approximating formula then is known as the trapezoidal rule, trapezoidal approximation. And now let's look at an example here and get all this chicken scratching off here. Look. Let's take a function, first of all, that we can check our answer on. And also something that Mr. Weissert can do our calculation on today. Alright, the thing that I want, the area of the region that I want to approximate is integral from 1 to 3 logarithm of x dx. Now this happens to be one that I'm well aware of, that we can get the capital F of x using one of our techniques. We will before this is over, but I want to use this for demonstration purposes. First thing you have to do in your approximation is pick what n is. So I'll pick n equal to 8. Delta x we haven't computed yet. Delta x then in this case will be, Mr. Johnson, what will delta x be if n is 8? What in general is delta x that we used all along? See, we're going from 1 out here to 3. If n is 8, what's delta x if I'm looking at this interval here?
1/4.
Pardon? No. Do I not 1/4? Oh, did you say 1/4? Oh, I'm sorry. I thought you said 24.
Well,
So you're multiplying the 3's or something. I don't know. 1/4. How do you get that? By 3 minus 1 divided by 8, which is 1/4. Sorry. So let's set up a little scoreboard here. First of all, we'll look at the xi. Then we'll look at f of xi. Then we have to have in here someplace 2 f of xi. Then we will have a column here for adding these up, since we have to add these things up before we take the half delta x. So if we set up our tabular form here, we'll have something like this. I think we'll be able to get it all on. So let's pick up, clear down the bottom. Oh, there we go. 1, 2, 3, 4, 5, 6, 7. And I'm going to actually have 9 values. This is when 0, 1 for I, 2, 3, 4, 5, 6, 7, and 8. That's why we have those 9 values here. Because we're actually starting out here at 1 is x sub 0. and 3 is x sub 8. Alright, so if we take this thing, we're looking at this function now, we know that the curve looks like this. Comes up through 1 at 0. This is the function y equal logarithm of x. We're actually approximating then from 1 to 3. We're breaking it up into 1.25, 1.5. So our x values would be, first of all, 1, 1.5, whoops, 1.25, 1.5, 1.75, 2.00, 2.25, 2.5, and finally 3. Now, what we want to do in turn then is get the VI's, the height or the parallel size length, and what would f of x sub 0 be? F of x sub 0. So this is the I values here. What's f of x sub 0? 0, yeah. Right, exactly what we said here. So that'd be 0. Now we block out this one because the f of x 0 we what? We do not double. So in this case our sum so far is 0. Right? Now what is f of x sub 1, which in this case is f of 1.25, or the logarithm of 1.25 that he's looking up on the table.
223.
Pardon? 0.223. Double that, 0.446. Why are we doubling that? Because that's this right here of our formula. Add up now our sum so far, 446. Second value then, at f of x sub 2, 1.5 would be 405, which is double that, 810. And our sum then in this case is 1256. 1.75 is what? 567. Oh. Double that, which is 1.120. Add that to this is 2.376. F at x sub 4, which is f at 2, is 0.693. Double that, you have 1.386. Add that to this, and you have 2673. Watch my calculation. Remember what time I'm in here. 2.25 then would be your next value, which would be 0.811. Double that one, and you have 1.622. Add that on, you have 4835. Now 2.5. 0.916. Double that, which is 1.832. Add that on here, and you have 2, and about a 7. Check me on that. Right? Now, before I do this and wreck everything, I'll put a line through that. Why did I put the line through that, Mr. Johnson? Because we're up to here now. So we only have that single value, which logarithm of 3 is
1.1.
Why did you want to set your line?
no wonder we moved up here so fast. Nobody heard yet. 2.75 and finally 30. 2.75 is what? 1.01. Now we have to double that one. 2.02. Add that on. 9.236. Now, the value of 3.
1.10.
1.10. Don't double that still. Add that on, we have 10.336, right? So the approximate area under this curve from 1 to 3 will be gotten when we figure out del x. Now what we have to do with del x? Divide that by 2. So del x divided by 2 is 1/8, right? 1/8 or 0.125. Multiply 10.336 by 0.125. What do you get? Area of the region then is approximately what? What's the approximate? It's all right.
I was checking your adding.
All right. Oh, okay. The area of the region then is approximately 0.125 times 10.336, which gives us approximately
6.67.
6.68.
6.68.
Yeah. 1/8 of that can't be.
Oh, 1/8, okay.
Yeah.
It's 1.25.
No.
Okay, right. 1.29.
1.29.
Sounds better.
That sounds a lot better. So I think it's best to set up the scoreboard here and not leave out any places like I almost did. Now let's look at how close this is for n equal 8 to several place accuracy. You erase all this calculation. Let's look at the antiderivative from 1 to 3 of the logarithm of x dx. What technique would you use to find capital F in this case, Mr. Ivan? Parts. In this case, you have exactly one choice for u and one choice for dv. You want to pick something, you can take the derivative very easily. Here and dv, something you can find the antiderivative very easily. And you only have one choice in each case here. Mr. Rouse, what are you going to pick for you? ln of x. Leaving us dx for this, which leaves us then v is, Mr. Lee, what's v? Right. And then du is, Mr. Johnson? 1 over x dx. So our actual valuation then is x logarithm of x minus, by integration by parts, x times 1 over x is 1, so you simply have dx. So the value then is x logarithm of x minus, Mr. Lee's my local authority on that, so antiderivative of dx is, just had it recently, x. Yeah. Evaluated then from 1 to 3. We'll actually do this calculation. Evaluated from 1 to 3. 3 then gives you, for the upper value, 3 logarithm of 3 minus 3. Subtract from that the value at the lower value. Logarithm of 1 we recently found out is 0, so that drops out here. And we have a minus 1 in here. So we have 3 logarithm of 3 minus 3 plus 1. Or, quick calculation, 3 logarithm of 3 subtract 2. And you guessed it, Mr. Weiss.
1.30.
1.30. So, how many places is that thing? That's 6 or 7 places.
Oh, yeah. Okay.
I just was rounding because.
Oh. No, not, we round over here. We round over here.
Yeah, okay, 1.2958.
I like that better. 1.2958. So, not too bad for n equal 8. And if you have a computer, and you're not worried about making this big box score out here but letting the computer do it, then you don't care if n is 108.
That could be 1.292 also.
This thing here?
Yeah.
Which is not bad. It starts the third place to be off a little bit. Now, depending on whether you're going in orbit and you want to get back to Earth, you worry about those third places. And you worry about rounding off, approximating this way. In other words, if you're up there in orbit, you hope that they're using a computer that has about 16 place accuracy so that you will go in the ocean and not on the land, or vice versa, depending on which type of space shuttle they have. So, not a bad approximation. Not a bad approximation. And this is just to have a check. Tomorrow, we're going to come up with another technique which will check the trapezoidal rule. I want to look at one now where we actually don't know the anti-gravity. We're going to evaluate it today and then check it tomorrow. So let's get that machinery in view. Any questions on this thing here? What's happening when we're looking at the trapezoid? In other words, a better approximation to a rectangle, if you're actually going to break it up and use the approximation, is the trapezoid. One that's even better then is not to approximate a curve with a line, but to approximate a curve with what? Would be a better approximation, Mr. Short. What would be better to approximate a curve? See, what we're doing essentially is taking that curve and saying, well, it acts like a straight line in there when we're looking at that trapezoid. What would be a better approximation?
An arc.
Pardon?
An arc.
An arc. All right. That's the next approximation. We're going to take a few checkpoints in between there and approximate a curve with a curve. And our favorite curve that we used all quarter is a parabola, and that's exactly what we're going to do tomorrow. But first, we have to set up the machinery so we can have something to check it with tomorrow, because we aren't going to have the luxury of the calculation like we did here with this function. In other words, you people being very pragmatic, you have to convince you that there is an approximation that's close before I get you to even stay awake at 8 o'clock. So let's look at the function that we do not have a nice anti-gravity for, but without the IBM 360 or something like that to do our calculation, just Mr. Weisert's rounding off the 3 places to keep things close, knowing that he's not going to go in orbit in this equipment. Let's look at the following situation. A lot of people have been wondering, what is the area under the curve from 2 to 5 of the square root of 1 plus x cubed dx? A lot of people have been writing in about that one, and we want to get that one approximated. We want to check it that it is accurate in several places. And in this case, to make it easy on ourselves today, since we don't have all that much time left, you guessed it, let's let n be 6. Which now give you a chance to see if I'm awake now. John, delta x then would be 1/2 or 0.5. So our scoreboard over here would look like this: xi, f of xi, twice f of xi, and the summation as we go along. And now I'll hope I have enough back. Here I'm going to let I be 0 and not count those things. Lo and behold, it comes out right. So now as we look at this table from 2 to 5, we're breaking it up into subintervals. There'll be 6 of them. X x sub 0 then in this case will be 2. X sub 1, 2.5, 3, 3.5, 4, 4.5, and 5. Now, not quite as easy here. What do we have for the f of x 0? It's the square root of, so f of 2 is equal to the square root of 1 plus, oh, what's so bad here at the beginning? What is it, 12 place accuracy in that way? 3. Rule out the doubling, so our sum so far is 3. Now life gets a little more hectic. F of 2.5 is the square root of 1 plus 2.5 cubed.
16.625.
16 point what?
625.
625, the square root of that? Oh, you didn't take the square root of that. All right, nobody heard it. See, that's why at all times you check your approximation and make sure that they're hitting all the buttons over there. See, even in this computer age, you're only as good as the person who's pushing the button.
4.07.
A lot of pressure on you, right?
Yes.
4 point what?
0.77.
0.77. It's going to help you. All right. Double that, which is 8.154. Add that, I think I can do that one. 11.154. Now at 3, what do we have? Taking square root as the last operation.
Square root.
5.29.
5.29. Double that. You have 10.58. I think if you could narrow it down to 1 place accuracy. So what? Adding that on, we have what? 21.734. Is that a winner? Okay, and using 3.5 and cubing it, adding 1 to it, taking the square root. By the way, you're going to get a chance to do this while he's doing his calculation. Remember the one problem on the test that I told you not to calculate step and integral? It's got E in it. You're on. 6.62. Double that. Well, 13.24. Add that thing on. And you have 34.974. Winner? 6.4.
7.4.
Calculator loses again. We'll try 2 out here. All right, so now at 4. Keeping in mind that tomorrow we're going to check this, and so everyone will want to have their handy-dandy calculator with them, and time is fleeting, but we're still making
8.06.
8.06. Now, for doubling that, 12.12, which gives you 37.094. Is that a winner?
16.4.
Oh! Get too many juices wild. 16 point. Getting lazy here. Better keep that thing separate too. All right, now we get what? 51.094. Is that better?
9.60.
9.60 and 19.20, and looks like we're going to be able to get a 70.694. Is that a winner? Better put my X in here, or I'll be sure to double that. The inertia, which is the next thing. Is that right? What do we got for 5 now?
11.22.
11.22. Which added on gives me
70.6.
2.94.
oh, it's 294. I think I want to turn back over here instead of there, but excuses are for people in Montreal. All right, so then we have here point, I got that right. 81.5 what? 14. Now what are we going to do with that 81.514 to get our approximation for this now? Mr. Robinson, what will we multiply that by? In other words, so far we've gotten this part here. Now we have to, all right, and delta is 1/2. 1/2 of 1/2 is 1/4 then. So we got to take 0.25 times 81.514.
20.3785.
All right, so 20 point what?
378.
How much of that is really worth writing down after we did all that? 2 places is a little bit probably ambitious. So we'll be looking at this tomorrow as our checkpoint. Now we got 5 minutes here. First of all, any questions? Seems that on the test there was a couple problems that had trouble setting up, so let's look at that just for the last few minutes. Going. We'll be back at this one tomorrow and use our next approximation to check this. So be sure you have this with you tomorrow at 20.37.
We're going to meet tomorrow on that.
That's tomorrow is Thursday. We are not going to meet.
Wednesday.
Not going to meet. I say by definition tomorrow is Thursday. But we're not going to meet on Wednesday. You got that. Yeah, we'll meet on Thursday and Friday. Tomorrow, I know you just hop up and run over here, but he'll have to tell you that, no, I'm not. First problem is the pumping problem. And in that case, we had what? A right circular cone that had a radius at the lip of what? 4? That's the one? 4. Radius was 4. H was what? 10? Right? And the work done in pumping that out is basically force times distance. So we've got to put both of these things in. And in this case, what interval did you have there, Mr. Ivey? I think you had set up right. Interval? Yeah, just give me the interval that you have.
From 10 to 0 to 10.
0 to 10. And you could put the constants in there, gravity and density. We'll leave those outside then.
And y times 4/25 y squared dy.
Now, question is, where does all this come in relative to force and distance?
There's also pi out.
Pi out front, okay. Now, first of all, if you look at this thing here and take the cross section, then you have 4, you have 10. Then if you take a representative slice of volume out of there and use the dy then as the thickness, if you take that slice out and look at it, you've got circle, right? Circle, the way we have it then would be what? Radius would be x, right? And the volume then would be the area of this times the thickness. So the area of this would be pi x squared. Then, so that's the area of that thing. Then the volume of that slice there would be pi x squared dy. Right? Now the question is, if we're integrating with respect to y, so we have to get x in terms of y. X is a function of y. So we go over here and look at this triangle here, which would be gotten by taking this slice out of there and just look at the top part of that. So that would be your x, right? This would be your y. And these are two similar right triangles. So the ratio is what? X to 4 as y is to 10, right? So x is 4y over 10, or 2/5 if you want to write that. So here's your x squared replaced by 2/5 y. Your dy and your pi for the constant of the area. Now this y is from what? That's right. It's just going to be your distance that is pumped. And it's going to vary from what? Pumping at 0 if it just goes over the lip to 10 if it goes all the way from the bottom. So there's your total work done. And you guessed it. You can evaluate that.
Why, okay, if you go from 0 to 10 though, what, 0 is at the top, right? Top to bottom? And why wouldn't the bottom be negative?
It's a good point. In other words, what was your coordinate system? And it brings up a point whether or not we can use y here, or we can use 10 minus y. And that's what it really is. This is where I think you made a mistake. It should be 10 minus y. You want it. So this thing here is not the distance, it's 10 minus y. In other words, if you start down here at 0, then what? Or if you start up here at 10, upper value, bump it to 0, and total then is going to be 10 if you're pumping it. So I think that yours probably is narrow. So yeah, this thing here. And I think Cyril, that's not Cyril. People didn't get it set up. So evaluate this with this thing here. You're right, you have the other coordinate types. What you have to do if you want to use the y value is to use the other coordinate. I think this is the same. So there's the integral, and I'd like you to evaluate that, not turn in the problems, and I'll give you the problems. But the one that really had trouble with was the pressure, or force on a dam. In this case, we had a circular cylinder, and so all we had to do was look at the face of it. Its diameter was what? 12, right? Now, most people couldn't get the function out of it. It was only half full, so there was water down here. We want to get the pressure on that face. Even though there's two faces, it doesn't make any difference how long that is. Basically, just the pressure on that one thing can be computed. The hint here, then, is what's the function? Well, if this has diameter 12, then it has radius 6. And you're looking at a semicircle. If you want to make it easy on yourself, make the origin the center. Then you have the circle x squared plus y squared equals 36. If you're looking at the bottom half of that, you're looking at the function, bottom half of this thing here, which would be y equal to the negative square root of 36 minus x squared. And here's where most of you couldn't get started on that. We'll see if you can get it now by Thursday. I haven't missed anything. We'll see you Thursday.
You mean that taking the positive pressure root?
Well, you still use the negative square root because you're going to be looking at this part down here. Thank you very much.
You want to turn those quiz problems tomorrow, right?
turn them in tomorrow sometime, you just come by, if I'm not there, put them under the door, or give them a secretary and put them in my box.